Hello. So in our last lecture, we ended up looking at the theorem for Lyapunov functions, and then I said that we're going to do some examples. So I just want to remind you of the theorem, which is here, that to construct a Lyapunov function, you make sure that it is 0 at the equilibrium point and it is positive away from it, and that you have to find the total derivative of the function. From the total derivative, depending on the sign, right, of the total derivative, then you can conclude whether the equilibrium point is stable, unstable, or asymptotically stable. All right. Also note that the total derivative here is given by this. The total derivative is actually the partial derivative of v with respect to, the independent variable, then the x1, the t, and so on. Okay. So this is how you compute the total derivative. So the example 1 is given by this nonlinear system. You are given the Lyapunov function v, which is equal to x1 squared plus x2 squared. Now we know that 0, 0 is an equilibrium point of this, right? If I plug 0, 0 here, this right hand side is 0, right hand is 0 here, right hand side is 0 here as well. So this is the equilibrium point. Question is that using this function, this Lyapunov function, can we explain, can we, I should say, determine the stability of this equilibrium point? So all you do is that you find the total derivative of the Lyapunov function. In this case, it's given to us, so it's kind of straightforward. So do that, find the total derivative, and after some manipulations, you should come up with an expression that looks like this. Nice looking expression. Okay? Now note that when r is equal to 0, if this is 0, then this guy is positive, this is positive, so the whole total derivative is strictly negative, which means that when r is 0, the equilibrium point is asymptotically stable. Okay? Now if r is not equal to 0, if this is not equal to 0, then we see that if x1 squared plus x2 squared is less than r2, then this thin expression in the second bracket is negative, but this is negative here, so the whole thing becomes positive. So v star is positive, which implies that if this x1 squared plus x2 squared is less than r2, then the trivial solution is unstable. Okay? From the theorem. Okay, my question is, why can't we consider the case x1 squared plus x2 squared greater than or equal to r squared? Why can't we consider this? We only consider this. All right? Good. So think about that. Now, the second example is given by this other nonlinear equation, nonlinear system, right, which is given by this. We want to determine the stability of the equilibrium point 0, 0 using the Lyapunov function, which is given by this. Okay? So how do you go? Again, the procedure is find the total derivative v star, which is equal to dv dx dxt, partial v partial y dy dt. But dx dt is actually x dot, dy dt is y dot. So find the derivative of v with respect to x. From here, we have 4x cubed multiplied by x dot is given here, which is this. You do the same for the y, you add them up and it's equal to 0. According to the theorem, if the total derivative goes to 0, then the equilibrium point is stable. So using this, we see that the equilibrium point for this nonlinear system is a stable equilibrium point. Then we'll look at the final example, which is given by this. This is a more interesting one, a little more challenging than the previous ones. Here, you want to construct a Lyapunov function of this form. So this is a form you are not given directly. You don't know C1 and C2. So you want to construct it, and after constructing it, you want to use it to determine the stability of the equilibrium point, the 0, 0. So this is the system. How do you go about it? Excuse me. You do the same thing. You have your v is given here. Compute the total derivative. So dv du1, du1. This should be total. This should not be partial. Should be du1 dt. This should be the same thing, which is this. Okay. But u1 dot is from the system, which is given by this. You go back to the system. u1 dot and u2 dot are it. So you plug them in. simplify it and you come up with this. Okay, now you can group terms and have this. Now this is important. Note that the conclusions of the theorem are based on the sign of the total derivative. So you want to be able to tell the sign based on C1 and C2. But that is easy to do when you have even powers of these, right? Or if their powers are odd, quite challenging. So in this case, because of this, it's not easy to determine the sign of V star. So what you do is that you equate this to 0, then you can get rid of this term. So when I equate this to 0, I get C2 is equal to 2C2. But because it's 0, V star reduces to this. And so now it's much easier to determine the sign of V star. Okay? So now I can see that if C1 is positive, okay, then C2 will also be positive. So both C1 and C2 are positive implies that my V will also be positive away from 0, 0. And that is a requirement for the construction of a Lyapunov function. We want the function to be positive away from 0, 0. Okay? So here I choose C1 to be a positive function, and that will make my V also positive. Now if C1 is positive, then away from the origin, I see that V star will also be what? Positive. And so I can analyze it from there. So if when C1 and C2 are positive, this guy, the Lyapunov function, will also be positive, which is good because that's what we need. But if C1 is positive, then V star will also be positive. But if the total derivative is positive, then by the theorem, then the equilibrium point 0, 0 is unstable. All right? So it's unstable. So we have constructed a Lyapunov function, which is given by this. And then we choose C1 to be positive. Note that we can't choose C1 to be negative. If we choose C1 to be negative, C2 will also be negative. And if you go back, if C1 and C2 are both negative, your V there will be negative away from the origin. But that is against the first statement of the theorem. All right? We want V to be positive, not negative. So that is why we can't choose C1 to be negative. It has to be positive, so that the Lyapunov function is a positive function away from 0, 0. Okay? Once you do that and construct it in a nice way consistent with the theorem, then you can draw your conclusions based on the total derivative V star. Okay? So in this case, it is unstable. Great. So now, this is an exercise that you should do. You do both of them. Here for the following system, we want to construct a Lyapunov function of the form this to determine whether the trivial solution is stable as asymptotically stable or unstable of these two systems. You have this, and you have that. So you try it, okay? So all the best. I will set it up on Sakai for you to formally do it and submit it. Okay, so I'll probably come back to you again with some other information. All the best.